All right, welcome back to The Explainer. Today we're talking about something pretty incredible, how physicists have managed to weaponize the very building blocks of the universe to save lives. We are diving deep into the physics of radiation therapy, where these tiny subatomic particles literally become soldiers in the fight against cancer. So that's the big question, right? How do you fight something you can't even see, like a tumor, with a weapon you can't feel? It sounds impossible. The target is buried deep inside the body, and the weapon is just, well, it's a beam of pure energy. The answer, as you'll see, is all about mastering the fundamental rules of physics, and then applying them with just an insane level of precision. Okay, so let's start with section 1, the precise problem. We've got to understand the challenge before we can appreciate the solution. You know, when you boil it down, the goals sound simple enough. You want to deliver a knockout punch of energy right to the tumor. But here's the catch. You have to do it while completely protecting the healthy tissue that's right next to it. We're talking millimeters away. It's like trying to demolish one specific building in a crowded city block without so much as cracking a window on its neighbors. It is a balancing act on a microscopic scale, and the stakes are, of course, as high as they get. So the weapons we're using are called ionizing radiation. That's just a fancy way of saying they pack enough punch to literally knock electrons out of atoms, and that's what shreds the DNA inside cancer cells. Now, these weapons come in two main flavors. You've got your directly ionizing particles, like electrons, which are like tiny little bullets that cause damage right on impact. And then you have indirectly ionizing particles, like photons. These are the high-energy X-rays we're going to be focusing on today. All right, section 2. Forging a radiation beam. So how in the world do you create one of these invisible weapons? Well, it's a two-step process. You gotta make it, and then you gotta aim it. Okay, it all starts inside this beast of a machine called a medical linear accelerator, or a LINAC for short. Seriously, think of it as a particle supercharger. It uses these incredibly powerful microwaves to rev up electrons to almost the speed of light. Now, you can use these superfast electrons directly, maybe for tumors closer to the surface. Or, and this is the cool part, you can slam them into a heavy metal target. All that energy has to go somewhere, and it gets converted into a powerful beam of photons. But a raw beam of energy is useless, right? It's like using a fire hose when what you really need is a surgeon's scalpel. So to shape that raw power, the beam has to pass through these heavy, dense metal blocks. They're called collimators. And they're all computer-controlled, moving in real time to sculpt the beam, basically creating a perfect energy outline that matches the tumor's unique 3D shape. We're talking pinpoint accuracy here. Okay, moving on to section 3, the subatomic collision. This is where things get really, really interesting. We've made the beam, we've shaped it, but what happens at that exact moment when that invisible energy hits an atom inside a cancer cell? Right. What actually happens? This is where physics becomes biology. It's the moment the magic happens. A single photon, which is just a little packet of pure energy, has to somehow transfer that energy to the cancer cell to do its dirty work. And it turns out there are 3 main ways it can do this, and it all depends on how much energy that photon is carrying. First on the list is the photoelectric effect. This is what happens with lower energy photons. The photon just gets completely swallowed up by an atom, and all of its energy goes into kicking an electron out of its orbit. Now, this is way more likely to happen in really dense stuff, like bone. And that's exactly why this is perfect for the X-rays you get at the doctor's office. The dense bone absorbs the photons, and that's why it shows up bright white on the image. Next up, and this one is absolutely crucial for therapy, is the Compton effect. The best way to think about this is like a game of subatomic pool. A medium energy photon comes in, smacks into an electron on the outer edge of an atom. The electron goes flying off, and that's what causes the damage. The original photon also ricochets away, but now it has less energy. For the kind of energies we use in therapy, this is the main event. This is the interaction we're counting on. And finally, if you crank the energy way, way up, you get something that sounds like it's straight out of science fiction. It's called pair production. This is where Einstein's famous equation E equals mc squared literally comes to life. A super high-energy photon zips past the nucleus of an atom and poof, it just vanishes. And in its place, pure energy transforms into pure matter. You get a brand new electron and its antimatter twin, a positron. Just incredible. Now this table, this is the secret sauce. This is why physicists are so obsessed with getting the energy of the beam just right. Just look at that middle row for medium therapy energy.
The Compton effect is responsible for, what, 94% of the action? It completely dominates. So by carefully tuning the LINAC to that exact energy sweet spot, they can make sure the energy is deposited in a really predictable, consistent way. It's what lets them essentially paint the tumor with a lethal dose of radiation, knowing exactly how it's going to behave. Okay, section 4, the digital battle plan. We've got the physics down, but how do you take all that theory and apply it to a unique, living, breathing person? Well, that's where you need a digital battle plan, a place where medicine, physics, and some serious computing power all come together. And that battle plan always starts with a super detailed 3D map of the patient. A CT scan is absolutely essential. It tells the planning computer how different tissues are going to interact with the radiation beam. Then you often combine that with an MRI, because MRIs are amazing at showing the soft tissues, letting you see the exact edges of the tumor next to all the healthy organs. You fuse those two images together, and boom, you've got a complete picture for the planning team.
This is where the medical physicists and dosimetrists come in. They take that digital map and slice by slice, they meticulously outline the tumor and every critical organ nearby. Then they start designing the attack, planning multiple beams coming in from all different angles, but all set to converge right on the tumor. It's brilliant. The computer then does thousands of calculations to optimize the shape and intensity of every single one of those beams, all to get the maximum dose on the target and the minimum dose everywhere else. And this number? This just says it all. 2 millimeters. That is the entire margin of error they have to work with. The isocenter, that single tiny point in space where all those beams have to intersect perfectly, has to be accurate to within 2 millimeters. I mean, that is less than the thickness of a nickel. The whole system, from the giant machine rotating around the patient to the patient's exact position on the table, has to maintain this absolutely mind-boggling level of accuracy. Okay, last section. Section 5, physics that saves lives. After all of this complex science, let's zoom back out and talk about what really matters. How does all of this abstract physics actually save a person's life? And really, this is the whole point, isn't it? Our deepest, most fundamental understanding of how the universe works, we're talking quantum mechanics, particle physics, the heavy stuff, it's not just for equations on a blackboard. Through some absolutely brilliant engineering and medical creativity, all that abstract knowledge gets transformed into a real, powerful, targeted tool that saves people's lives every single day. And I think it's so important to remember that behind all the machines, behind all the complex math, they're just people. This dedication, it's from the preface of one of the main textbooks in this field. And it's just such a powerful reminder that all of this science, it's driven by a really deep human motivation to take this abstract knowledge and turn it into real hope for patients and for their families. And this technology is never standing still. It's constantly evolving. We're getting new techniques, a deeper understanding of how radiation affects biology, and outcomes are improving every single year. It really just leaves you wondering, doesn't it? We've mastered the physics of today's medicine. What's tomorrow's going to look like? What other secrets of the universe are just waiting out there to completely revolutionize medicine all over again?